Another day, another story. Chaos theory is a branch of mathematics and physics that deals with complex systems whose behavior is highly sensitive to initial conditions, an effect popularly referred to as the butterfly effect. This sensitivity means that small differences in the initial state of a system can lead to vastly different outcomes, making long-term prediction practically impossible despite the deterministic nature of the system. Key concepts of chaos theory. Welcome to Tabo Eminent Channel. Deterministic systems. Chaos theory applies to systems that are deterministic, meaning they follow specific rules. However, because of their sensitivity to initial conditions, predicting their future states becomes incredibly difficult. Sensitivity to initial conditions, even a tiny variation in the starting conditions of a system can result in vastly different outcomes. This is famously illustrated by the butterfly effect, where the flapping of a butterfly's wings in Brazil could hypothetically set off a tornado in Texas weeks later. Strange attractors. In chaotic systems, patterns known as strange attractors can emerge. These are shapes in phase space that the system's state tends to follow over time. Unlike fixed points or simple cycles, strange attractors have a fractal structure. Nonlinear dynamics. Chaos theory is heavily rooted in the study of nonlinear dynamics. Nonlinear systems do not have a straightforward cause and effect relationship, making their behavior more unpredictable and complex. Applications of chaos theory. Weather prediction. One of the classic examples, since weather systems are highly sensitive to initial conditions, making long-term forecasting notoriously difficult. Population dynamics. In biology, chaos theory can explain fluctuations in population sizes over time. Economics. Financial markets can exhibit chaotic behavior, where small events can lead to significant economic impacts. Physics and engineering. Chaos theory applies to a range of physical systems, from fluid dynamics to electrical circuits. Chaos theory's story begins with a weather scientist, Edward Lorenz, in the early 1960s. Lorenz was running a computer simulation to model weather patterns, using a set of differential equations that describe how weather evolves over time. One day, while trying to save time, he decided to restart a simulation halfway through using rounded-off numbers rather than the precise values he initially used. He expected to get a similar outcome, but instead, the results diverged dramatically. This unexpected result showed that small changes in the initial conditions could lead to vastly different outcomes, a phenomenon that came to be known as sensitive dependence on initial conditions, or the butterfly effect. The butterfly effect is perhaps the most famous idea in chaos theory. The metaphor suggests that a butterfly flapping its wings in one part of the world could set off a chain of events leading to a tornado elsewhere weeks later. This doesn't mean that a butterfly literally causes a tornado, but rather that small changes can grow and have large-scale consequences in complex systems. The strange attractor and fractals. Lorenz's work led to the discovery of strange attractors, which are patterns that emerge when you plot the behavior of a chaotic system over time. The most famous of these is the Lorentz attractor, a set of equations that, when graphed, produces a shape resembling butterfly wings. Unlike simple attractors, such as a point or a cycle, strange attractors have a fractal structure, meaning they exhibit self-similarity at different scales. Chaos theory in nature. Chaos theory isn't just a mathematical curiosity, it's a phenomenon observed across various fields. For example, in biology, the chaotic behavior of predator-prey populations was modeled by the Lotka-Volterra equations. In certain conditions, these equations produce oscillations that are highly sensitive to initial conditions, leading to unpredictable fluctuations in species populations over time. Similarly, in cardiology, the heart's rhythm can sometimes exhibit chaotic behavior. Under normal circumstances, the heart's beating is regular and predictable. However, when it enters a chaotic state, such as during atrial fibrillation, the rhythm becomes irregular, and the precise prediction of beats becomes impossible. Chaos in everyday life. The principles of chaos theory extend to more mundane aspects of life as well. Consider the stock market, a system where countless factors, from investor behavior to economic indicators, interact in complex ways. While analysts try to predict market trends, the chaotic nature of this system means that small, seemingly insignificant events can lead to large market swings, making precise prediction notoriously difficult. Weather is another daily example. Despite advances in meteorology and computing power, weather forecasting beyond a week becomes increasingly uncertain due to the chaotic nature of the atmosphere. This is why weather predictions, while relatively accurate in the short term, often become unreliable over longer periods. The legacy of chaos theory has fundamentally altered our understanding of the universe. It has revealed that not all deterministic systems are predictable and that the universe has an inherent unpredictability. This realization has implications beyond science, influencing philosophy, literature, and even art. For example, the fractal patterns found in strange attractors have inspired artists and architects, leading to designs that reflect nature's chaotic beauty. In a broader sense, chaos theory has taught us to embrace uncertainty. It suggests that while we can understand the underlying rules of complex systems, our ability to predict their behavior is limited. This humility in the face of nature's complexity encourages a more nuanced approach to science, one that recognizes both the order and the inherent unpredictability of the world around us. The double pendulum and the dance of chaos. A classic illustration of chaos theory is the double pendulum, a simple system with two swinging arms. At first glance, this device seems straightforward, but once set in motion, it behaves unpredictably. The double pendulum's movements are governed by deterministic laws, Newton's laws of motion, to be exact. However, even a slight change in how you release it leads to an entirely different pattern of movement. Unlike a simple pendulum, whose motion is predictable, the double pendulum showcases the core of chaos, deterministic yet unpredictable. The double pendulum has been a subject of fascination for physicists and artists alike. Its chaotic motion creates patterns that are as beautiful as they are bewildering, illustrating how chaos can give rise to complexity and order in unexpected ways. In many ways, it serves as a metaphor for life itself, where outcomes are influenced by countless variables, making the future uncertain yet full of possibility. History. The study of chaotic systems began in earnest with the work of meteorologist Edward Lorenz in the 1960s. While running weather prediction models, Lorenz discovered that minute changes in the input conditions resulted in vastly different outcomes, leading to the understanding that even deterministic systems can behave unpredictably. In essence, chaos theory provides insight into the complexity of nature and the limits of predictability in dynamic systems. Thanks for watching. Request you to subscribe the channel.